In the next series of lectures, we're going to talk about reaction mechanisms. Now, this is personally my favorite part of this quarter. So I hope you also enjoy it. And I understand if you have a different favorite part of the quarter. But here we're going to take kinetics, which is honestly a relatively dry topic within chemistry. And we're going to apply it to reactions to start to understand the individual elementary steps that take place for a transformation to occur. And so this feels like you're seeing the kind of step-by-step slow motion of a reaction by digging into the reaction rates, which can make that kind of dry material seem way more interesting. And we can apply this to really interesting problems that we see in chemistry. So lots of transformations that we would like to see occur or chemical reactions. We actually look to nature to learn about. And by studying the mechanisms of enzymes and biological processes that have been refined through evolution over an extremely long period of time, we can see how those reactions occur and then try to replicate them in a small molecule setting in a lab without big proteins, which is pretty interesting. So anyway, let's dive into this. So reaction mechanisms. A reaction mechanism is a series of individual chemical steps which in which an overall reaction occurs. So it's like the little steps that make up an overall chemical reaction that we're looking at. So mechanisms are going to be a series of what we call elementary steps. Elementary steps are chemical reactions that can't be broken down into simpler steps. It's similar to like two molecules colliding, one bond breaking, one bond forming could be an elementary step, or one molecule decaying into two would be an elementary step. A rate law and all the work that we just learned about to determine a rate law can help us understand the sequence of steps. If we know what an overall reaction is, we can propose a couple of different ways that might happen just based on what we've seen with other types of reactions. But by studying a rate law and developing one for the overall reaction, we can then figure out which of our proposed mechanisms is actually the one that's most likely to represent what's happening. So how about we walk through this with an example? So here's an overall reaction that occurs between NO2 and fluorine. And we have these two NO2 molecules and one fluorine molecule that combine into two NO2F molecules. Now, three molecules colliding in the right orientation with the right energy to form then two other molecules is a little unlikely. I mean, it might occur, it'll probably occur pretty slowly. It's more likely with that many molecules in our reactants that we really actually have a series of steps that are occurring. And so here are actually the elementary steps of that overall reaction. First, we do have two NO2 molecules and an F2 molecule collide, but they're going to not form these two molecules in our products. Instead, they're going to form only one of them. So we'll form. So our molecules collide, and our F2 molecule, that's really like this, that bond breaks, and one of the fluorines reacts with the NO2 and produces one of our product NO2F molecules. And we create this intermediate right here, F. Now, we can think of this overall, if we think about this in reaction, I feel like we can write this out two ways. And so I've seen this reaction's elementary steps represented as they're written here, where we have our fluorine as the intermediate, but we also think of everything that's in between as intermediates. And then that fluorine atom is going to then connect with the NO2 and form a second equivalent of our two NO2F. I actually think that, so this is how this is often represented in textbooks. A way that I think is a little bit more intuitive to think about it is that rather than having two of our NO2Fs and the F2 together in our reactants for our first elementary step, we really have just focus on the things that are actually reacting. And so we have NO2 plus F2 is forming NO2F plus F. And then that F molecule is going to react with another equivalent of NO2 to produce another equivalent of NO2F. And now we'll have two of those essentially. And so when we add these up together in our reaction, we get a total reaction that's 2 NO2 plus F2 forms 2NO2F, where our intermediate is just seen as this one fluorine atom that's alone. So reaction intermediates are something that form within the series of elementary steps and then are consumed. So that way they're not actually something you start with and they're gone by the time the reaction's over. And so an intermediate is something that you don't see as a reactant or as a product. It's just kind of these in-between steps where they occur. And so you might see this idea of elementary steps represented in either of these two ways. And the difference that I see between them is one is characterizing reactants that aren't reacting in the first step of the reaction, but they're including them. And so that difference there is where I would say there's just one NO2 that's actually doing some chemistry and colliding with that F2. This one is including both of those NO2 molecules and then leaving one here unreacted. And then taking our product that's formed from the first one and carrying it over into our reaction in the second step, but having it just not actually do anything. It's not actually doing any of the chemistry. And so what's really reacting in that second step is one of the NO2s and the F intermediate that is around. And so you'll see these both ways. This is a stylistic thing. I mean, I personally like my way better. That's on the side, but I want you to be aware of what you'll read in textbooks as well, especially introductory textbooks. So moving on, let's look at this in terms of a reaction diagram. I find this helpful. So this is what's happening. We start with all of our reactants together and we show those right here. We've got all of our reactants, great. And we're going to transform them into products, 2NO2F molecules. And along the way, we're going to form an intermediate. Which will be that one of our product molecules, NO2F, and then a fluorine and NO2. And so I think that the kind of textbook way of representing intermediates and these reaction steps is meant to go along with one of these reaction diagrams. And so they fit kind of better, where we have everything along the way and we form some products and then we form some more. And so I do think that's really helpful here. And so what you see with this reaction diagram is we're used to just one peak, one transition state. And we have two here because we have two steps occurring. So we have a transition state for step 1, and we have a transition state for step 2 of each of our elementary steps that make up this overall reaction that takes place. Now, our enthalpy is still in terms of our, here we go. Our enthalpy is still in terms of our overall reaction, comparing reactants to products. But our activation energy, now we have two of them. We have an activation energy for the first step, and we have an activation energy from the second step. Note that second step activation energy is going from the intermediate to the second activation energy rather than the reactants all the way up to the second activation energy. So it's just this energy right here compared to from the reactants up to the first one. And so we can see that that first step has a much higher activation energy than the second step. And so when we look at something like this, we always expect the reaction that has the highest activation barrier to be the slower step because it will require a larger amount of kinetic energy to have enough potential energy to overcome that activation energy barrier. And so we'll have fewer of our collisions that'll actually be able to overcome it and produce the intermediate. And so we expect that this first step right here is going to be slow compared to the second step, which we expect to be faster, just because that activation energy is so much smaller. All right, so what we can take away from that reaction diagram is that each step in the mechanism is essentially its own reaction. It has its own activation energy and it has its own rate law associated with it. And so our overall reaction is going to have a rate law that needs to be experimentally determined. We don't just sum up all of the ones from the elementary steps because they're going at different rates. But we can say from an elementary step, when we look at that, we don't need to experimentally determine the rate for that, or the rate law or the order of the rate law. That we can actually determine just from looking at the balanced equation or the equation of the elementary step. And really what we're deducing when we look at this is the rate law's order more than anything else. So we're getting the order from it, not necessarily the rate law constant. That we would have to have some experimental data about the dependence of the rate on the concentration. And so if we have, here's a list of different elementary steps that are common. So just one molecule splitting up into products or changing its configuration so it actually has broken and reformed bonds within the molecule is going to be a first order single molecularity reaction or elementary step. And so if we just have one reactant that is in our elementary step, we can have a rate law that is rate is equal to the rate constant times that concentration. And so that's going to be first order. Now, if it's two of the same, then we can say it's second order with respect to that reactant. And it might be that we actually have two different things that add together and collide that form products. And then we would have a first order dependence on both of those concentrations with an overall order of 2 for that elementary step right here. Now, three or molecularities of 3 or bringing together 3 molecules in an elementary step is much more rare. There's a number of variations of this. It could be one reactant with a third order dependence. It could be one with a second order plus another one, or it could be 3 first order dependencies on 3 different reactants. But these are less common and we won't see these as much. So we can look though and compare a proposed mechanism to an overall reaction and see if it's reasonable. It doesn't mean it's the correct mechanism. We would really need to experimentally determine that. But we can get an idea if it's reasonable by making sure that all of the intermediates are actually, in fact, intermediates and not left over as a reactant or product. And that your proposed mechanism elementary steps overall add up to the net reaction. So let's show how to do that here. So this is an example where we're going to confirm a proposed mechanism and make sure it's reasonable. And then the next step after confirming it's reasonable would be to actually get experimental data and confirm that it then matches what we're seeing in our proposed mechanism steps. So the way that we do this is we just add them together. And this kind of goes back to when we worked with Hess's law and we were manipulating equations and to determine enthalpies of reaction. Here, we're just going to add these together and make sure then that we cancel out anything that's the same on both sides. Now, all intermediates should be both a reactant and a product and not actually present in the overall reaction. So looking at this one, when we add these together, I'm just going to put everything that's on the left-hand side of the arrow in one line. So we'll have NO2 plus NO2 plus NO3 plus CO. And on the right-hand side, I'm going to put everything that's a product. So that's an NO3, an NO, NO2, and CO2. Now, the goal is to go through this and cancel out anything that's the same on either side and then consolidate. So if I've got 2 of something, I'll combine them. So canceling things out, I can see I have an NO2 and an NO2. So I've got 2 on my reactant side and I have 1 on my product side. So I'm going to cross off one of these. All right. Looking at my NO3, I have an NO3 on my reactant side and an NO3 on my product side. So I'll cancel those out. Carbon monoxide, I don't have that anywhere on the product. Now moving over to the product side, I don't have an NO or a CO2 on my reactant side. So my overall reaction becomes NO2 plus CO forms NO plus CO2. And that matches my overall reaction perfectly. So because these match, I could say this is a reasonable proposed mechanism. Like it at least sets up a mechanism that would create our overall reaction. So now what we would do is we would make sure that, or we would write out our rate law for each of these elementary steps, right? So let's do that in green. So for our first one, our rate law is going to be equal to some rate constant times the concentration of NO2 times the, and then it would be times the concentration of NO2 again. Because I have two NO2s, I will just multiply or put that to an exponent of 2, showing a second order dependence on NO2. So what we're going to do here is the exponent is always going to essentially be the coefficient in front of the molecule that we're looking at, the reactant. And this NO2 plus NO2 is the same as saying, you could also call this 2NO2 as well. All right, let's do the rate law for the second elementary step. This will be the rate is equal to the rate constant times the concentration of NO3 times the concentration of carbon monoxide. And that's it. And so there's just a first order dependence on each of these because there's a one coefficient and there's not multiple of those molecules combining. And note that I'm only putting in the reactants, right? Because we're going to be looking at the concentration of our reactants to dictate the rate of the reaction. And so we have just our reactants. In the case of the second step, I have only intermediates actually that are included in my rate law. And those aren't something that I would know an initial concentration of because that concentration will form as the first step takes place. So that isn't something I'm going to be able to measure in a predictable way. I'll be able to find evidence of it. I might be able to track its concentration if I'm lucky, but it's not something that I'm going to be able to have control over the way I would an initial set of reactants that I can like make sure I'm pouring a specific amount into a beaker.